Hey there, and welcome. Have you ever looked outside during a huge thunderstorm and thought, what is the recipe for something like that? Well, today, that's exactly what we're going to figure out. We're going to break down how a storm gets made, all the way from a single ray of sunshine to a massive thundering cloud. Seriously, have you ever just stared up at one of those big, dark, swirling clouds and wondered what in the world is going on up there? It's not just a bunch of fog, right? Well, that's our destination today. We are going on a journey high up into the sky to see exactly how these incredible weather machines get built, piece by piece.
You know, every story has a beginning. And for a storm, that story starts with one single, incredibly powerful ingredient that fuels everything else. And that is, of course, energy from our sun. It's the spark that lights the fuse for basically all weather here on Earth.
So it all kicks off when the sun shines down and warms up the Earth's surface. We're talking the ground, the oceans, even a little puddle on the sidewalk. This heat is what we call thermal energy, and you can really think of it as the engine for all weather. It's the raw power that gets the whole process moving.
And here is where that thermal energy really gets to work. It zaps these tiny water particles with a jolt of energy, turning into what we call kinetic energy. And that's just the energy of pure movement. All of a sudden, those little particles aren't just sitting still anymore. They're vibrating, they're buzzing, and they're getting ready to make a run for it.
So with all this brand new energy, our little water molecule is about to go on an absolutely incredible adventure. It's about to leave the ground behind and start its climb, way up into the atmosphere.
This whole trip upwards basically happens in three main stages. You can see them here. First, our water molecule has to escape. Then it needs to catch a ride going up, and finally, it's going to meet up with millions of its friends to start building something totally new. Let's break each of those steps down.
And this first step, this is the great escape. That kinetic energy gets so intense that our water molecule literally breaks free, changing from a liquid into an invisible gas called water vapor. Poof! It's now so light it just starts floating up and away. So, how does it get all the way up there? Well, it hitches a ride on something called an updraft. See, when the sun heats the ground, the air right above it gets warm, which makes it lighter, less dense, and that causes it to rise. Our little water vapor molecule gets swept up in this current. It's like stepping onto an invisible elevator that's going straight up. But it's not a one-way street up there. This slide really shows the two opposing forces that are always at play. While our molecule is riding that warm updraft up, there are also downdrafts, currents of cooler, denser air that are sinking back down. This constant cycle, this sort of atmospheric dance, is what makes our weather so incredibly dynamic. Now, as more and more of these water molecules make their escape and start rising, the air starts to fill up with all this water vapor. And we've got a word for that: humidity. You can kind of think of the air like a giant sponge. On a really humid day, that sponge is getting pretty full. Okay, we've made the climb, we've arrived at our destination, and now we get to the most dramatic part of the whole story. Way up here in the atmosphere, all of that invisible water vapor is about to go through a massive transformation into the visible, powerful thing we know as a cloud.
You see, the higher that water vapor rises, the colder the air gets. This big drop in temperature causes the molecules to slow way down and start huddling together for warmth, changing from a gas back into tiny little liquid water droplets. That process is called condensation. And when billions and billions of these droplets get together, a cloud is born.
Okay, now our brand new cloud is still climbing, and it's about to hit a super important number, the freezing point, 0 degrees Celsius or 32 Fahrenheit. At this point, the rules of the game totally change. This is where liquid water is about to become solid ice, and the storm really starts to build some serious power.
And check out how this happens. A tiny water droplet freezes into an ice crystal. Then, those powerful updrafts inside the storm cloud act like a roller coaster. They toss this little baby hailstone way up, where it collects more water, then it falls a bit, then it gets shot right back up again. And every single trip it adds another layer of ice, getting bigger and bigger and bigger.
Sooner or later, these hailstones get so big and so heavy that those updrafts just can't hold them up anymore. They overpower that invisible elevator and start to fall. And when this happens on a massive scale, that's when we get hail, a powerful thunderstorm finally unleashing all that frozen cargo.
Well, what goes up must come down, right? This brings us to the final chapter of our water molecule's epic journey. After being totally transformed inside that cloud, it's finally time to make the trip back down to Earth. This whole return journey has a general name you probably know: precipitation. It's really just the umbrella term for any form of water, whether it's liquid rain or the solid hail we just made, that falls from the clouds. It's what completes the cycle and brings our water molecule all the way back home.
But hold on, let's zoom out for a second. The storm cloud we've been following, well, it didn't just pop up out of nowhere. It's actually part of a much, much bigger system. An invisible player in the game called an air mass. We're talking about a huge body of air, sometimes thousands of miles wide, that has its own unique temperature and humidity.
And this is where the real action happens. The most powerful weather, including the thunderstorm we've been building, almost always forms at what's called a front. This is the boundary line, the collision point where two totally different air masses smash into each other. A warm, humid air mass clashing with a cool, dry one, that is the ultimate recipe for a major storm.
So, it's one thing to understand the recipe, but how do we actually use this in our day-to-day lives? Well, let's take a look at how we can read all these atmospheric signs to predict what the weather story might be tomorrow or the next day. Right. This is where forecasting comes in. A weather forecast is basically humanity's best attempt to read the end of the weather story before it even happens. By gathering all sorts of data and using these super complex computer models, meteorologists can tell us if the conditions are right for another storm to get brewing.
And one of the biggest clues they look for is a change in air pressure. What is that? Well, it's the invisible weight of the entire atmosphere pushing down on us all the time. When a low-pressure system moves in, it's a huge clue that air is rising, and that's a key ingredient for the clouds and storms we've been talking about.
So how do we measure this invisible pressure? Well, the tool for that job is the barometer. This little instrument lets us see those invisible changes in air pressure. A falling barometer is a classic sign that a front is moving in and the weather might be about to get interesting. It's kind of like getting a sneak peek at the next chapter of the story.
So there you have it. We've traced the entire journey. We've learned the basic recipe for a storm, from a single sunbeam all the way to a hailstone. And that leaves us with one last, really important question. In a world where our climate is changing, what happens to the weather when we start fundamentally changing the ingredients themselves?